Okay, so we're doing 7.3, which is very similar to 7.1 and 7.2. Again, this shouldn't be a huge problem. It is a new concept. What we're going to be talking about is e, which is basically a different form of the exponential function. So what we started with was we have y equals ab to the x. That's what we were dealing with before. So basically what's happening is e is just a number. E is a number that a mathematician figured out a long time ago to represent an exponential function. It's called natural base e. So essentially what's happening is e is equal to approximately 2.718281828, kind of like pi. So it's one of those numbers like pi where someone has figured out that this is very useful in certain things in math. So what our function now is turning into, so before it was ab to the x, where b could be any number greater than 1 or in between 0 and 1. Now what our function's looking like is y equals a e to the x. Now there are other things that are going to be put into this, and you're going to see that below with our key concept. But the idea is e is a number. It's not a letter or a variable. E is a number. Okay, up here b was a variable, or b is an unknown that we don't know. There's no number attached to b. Whereas if you see e, then it equals this number right here. So real quickly, just to show us what we're dealing with, nothing has changed. So if we have 2e to the negative 3 times 6e to the 5, we could put this in our calculator and get a number, but we won't. We're going to do the same thing we've always done. 2 times 6 is 12, and then we do negative 3 plus 5 is 2, so we have 12e to the 2. Okay, so that should not be a problem. You're not going to really deal with that much, but I just wanted to clarify that if you do see something like that you can combine them like you would regular exponents, things like that. Okay, so let's move on to what the graphs look like, and you'll notice that the graphs look pretty much exactly the same as they did before. The difference is now is we have y equals ae to the rx. So almost exactly what I wrote above, except now what we're doing is we're putting an r in front of our x. So sometimes you're going to see your exponent is multiplied by something, especially when dealing with e functions. So what we have here is if a is greater than 0, so if a is positive, and r is greater than 0 as well, then it's going to be an exponential growth. So now, because e is always positive, our r is going to determine whether it's going to be an exponential growth or exponential decay. Because if r is positive, we will have exponential growth. If r is negative, then we're going to have exponential decay. Okay, and again, the functions look exactly the same. Our y-intercept is 0, 1 on both of them. The only way it changes is if our a changes. A always determines our y-intercept. If it's y equals e to the rx, then a is just 1. So we have 0, 1. And then our second point, in the base function, it's going to be 1, e, which is 2.718. But what we're basically going to be doing is, because these functions are always going to be different, is we're going to be plugging 1 into our function to see what that second point is. So there's no way for us to just magically figure out what it's going to be without plugging it in, because e is such a weird decimal. So that's what you're going to see me do when we actually graph these, is we're going to plug it into a calculator, which I've done ahead of time. But that's what you'll be doing when you graph these, is putting in 1 into your function and then figuring out what your decimal answer is using a calculator. So let's get right into this. So 2e to the 0.5x. Well, again, the number out in front of the e will determine our y-intercept. So we already know from the start that 0, 2 is our y-intercept. Okay? And then what we're going to do is we're going to plug this value in, and we get 3.1 something. So our other value is 3.1, so I'm going to plot that. And again, all you're doing is plugging 1 into this function and figuring out what your decimal is. And then you just draw. Okay, very, very similar. Okay, domain and range, which we're also being asked to write down, same thing as before. We're dealing with an exponential function, so we have all real numbers as our domain. That's because x can be anything. And our range is the same thing. It's going to be anything where y is greater than 0, because we have an asymptote here at y equals 0. Okay, so now moving on to this one. Again, same idea. What I'm looking for you to do is I know that we're going to do our parent function first. So I'm going to do the parent function in red. So we have 0, comma 1.5 as our y-intercept. And to figure out what our 1 value would be, again, we plug it in and we get 1.9 something. And again, it doesn't have to be perfect. And we know that our parent function will have an asymptote of y equals 0 again. That is a really bad graph. Let me redo that. Okay, so 1 and then 1.9. So let me connect these. Yep, that's terrible. I'm not redoing that again, but you guys get the idea. It's hard to do on this Mobi. Okay, but again, all of our points that we start with any of our parent values will always have a range of y is greater than 0. The asymptote is at y equals 0. So now that we have these 2 points, though, that makes it easy for us to shift. We have x minus 1, which means all of our points are going to shift 1 to the right, and then our minus 2 is going to shift them down. So we have, oh, I'm sorry, I messed that up. Of course, when I redid it, I messed it up. So that was supposed to be 1.5 because of this value right here. So I'm going to go 1 to the right and down 2. So my new function, which I'm going to graph in black, so we went 1 to the right and down 2, so we're at negative 0.5. And then again, we went 1 to the right and down 2, so we have a point right here. So what you can see is from the parent function, we should get the same shape graph that we had before. And again, I'm having trouble drawing a smooth curve, but again, you get the idea. It's still an exponential function. And now our domain still stays the same, all real numbers, but our range now changes, and our range is always based on this value. Over here, it's almost like saying plus 0, which is why we have y is greater than 0. Here, because it's negative 2, it's going to be y is greater than negative 2. And obviously, if that graph was opposite and it went down, then it would be y is less than negative 2. It shouldn't be that complicated. You're just looking at your graph, you're looking at how you shift it, and whatever you shifted it, our new asymptote is at that new value. Okay, so we know it's going to either be y is greater than negative 2 or y is less than negative 2, depending on whether the graph is going up or whether the graph is going down. Okay, so hopefully that makes sense. Let's move on to the back side of the page. That's the graphing portion of it. Again, I don't think it's that difficult. We're just dealing with a different type of function with e, and we're going to be relying on our calculator a little bit more for that. All right, so looking on the back side, we do have a continuously compound interest. So this is the same idea of what we did before, except now we have a function that's PE to the RT. So P is still going to be our initial, R is going to be our interest rate, and T is going to be the number of years. The difference between this is compounded continuously. So what I'm going to do is I'm going to go through 3 examples. And what I want to do is I want you to use these 3 examples to be able to figure out how you know which equation you're going to use and how you're going to use that equation. So here in this first one, it says we're depositing $2,500 into an account that pays you 5% annual interest compounded continuously. Find the balance after 7.5 years. The second one says deposit $2,500 in an account that pays you 5% annual interest compounded annually. Find the balance after 7.5 years. And then the last one, same thing, except we're going to compound it daily. So what's going to happen here is we need to be able to decide what we're going to do. So the only thing that's different about each one of these is this is being compounded continuously. This is being compounded annually. And this one over here is being compounded daily. So we will come up with our formulas. Anytime you see the word continuously, it means we're going to do A equals PE to the RT. So when we actually plug this in, it's going to look like 2,500 times E to the 0.05 times our T, which is 7.5. And again, you just plug that right into a calculator and you'll get a value. And our value is $3,673.48. So after 7.5 years, our $2,500 would turn into this if it was being compounded continuously, which you rarely see, but sometimes maybe. Okay, next one. So the next one says you deposit $2,500 in the account that pays you 5% annual interest compounded annually. So what that means is, that means we have to use our equation that is A equals P times 1 plus R over N to the N times T power. So the N represents how many times it will be compounded in a year. So because it's being compounded annually, our N is just 1 here. So when we plug this into our formula, it's going to be 2,500 times 1 plus 0.05, and then it's just going to be over 1. And then we're going to have a 1 up in the exponent as well. So it'd be 1 times 7.5 in the exponent. Okay, and then again, plug that into a calculator, and you get $3,604.62. Okay, so that's if you're compounding it annually. On the last one, where it's compounding it daily, what we have here is we have the same formula as we just used. P, and then we have 1 plus R over N to the N times T power. So because here we're compounding it daily, that means our N has to be 365. So our equation, or our formula, will look like this. 2,500 times 1 plus 0.05 divided by 365 to the 365 times 7.5 power. So again, it changes because of how we're compounding it. So maybe that will help you out from some of the previous ones. So in the book, sometimes it says it's always an annual interest. Almost always it should say an annual interest. But then it should tell you how it's compounding. How it's compounding is going to determine what your N is. So again, we plug this into a calculator and we get a value of $3,637.39. So if you looked at the three values, what you should see is this one gives us the biggest value because it's compounded continuously. This one gives us the second biggest value because we're compounding it daily. The more you compound interest, the more money you're going to get, or the more interest you're going to gain. And then this one's our worst one because it was only compounded once a year. Okay, so hopefully that separates those and helps you a little bit. That's going to be really important because when you get test questions, you need to know which formula to use. So I will see you guys tomorrow. Hope that helps. Hope that makes sense. Bring questions tomorrow.